look at that. We solve for our reactions. We're so smart. Okay, now we're going to move on to trying to figure out what members are in tension and compression and how much of those external loads and those reactions to those external loads are going to be transferred into the members. State whether they're in tension or compression. So I would suggest starting at a joint that has more knowns than unknowns, and so less members coming into it. We're going to start with joint A, do a free body diagram of joint A. Okay, joint A has got that normal force that's acting to the left with its 90 kilonewton magnitude on it. So there it is, look at it acting on that joint, that little dot, and there's two members coming into it, which we're going to assume are in tension. So we've got that force that's being transferred into member AB, going from joint A to joint B. And we've got another member coming into that joint, that one that's going from A to D. And we've assumed that they're in tension. And look at all these forces are acting at one point, concurrently at one point. So we can use our two equations of equilibrium, sum of the force in the X and sum of the force in the Y equal to 0. And just by doing a quick inspection, we can see that we can solve for that force in AD real quick. Like we've assumed it's in tension, so that force in AD is negative, and that normal force at A is also negative. They're both going to the left if we're using our rectangular coordinate system. So we can solve that real quick, and we can figure out that that force AD is negative 90 kilonewtons. So we guessed it was in tension. It came out negative, so really it's in compression. Cool. Then we've got some of the force in the Y still that we can use. Okay, we can do a quick little inspection. Some of the force equal to 0 because we're in equilibrium, and then that force in AB, it turns out to be 0. Crazy, eh? Okay, so we're just going to do a little summary here. And that force in member AB is 0. That force in AD is 90 kilonewtons in compression. Look at that. Do a little summary, just like we did with our notes. We have a tablet, so we can make it look pretty real quick. Okay, just rearrange this, highlight it, so then your reviewer doesn't have to go and hunt for those answers, and we'll just kind of make this smaller so we got some more room so that we can move on to our next joint. And I'm going to choose joint B just because we have our two reactions there, and we'll do a little free body diagram of that one as well. So here's joint B. Look at, got a little dot there, that's a joint. We're going to identify all the external loads that are acting on it. So those two reactions, BX with its magnitude of 60 kilonewtons, and that BY, that 45 kilonewtons going up, trying to keep it from falling down. And then we're going to go and again identify the members that are coming into it in tension. Just, we got to start somewhere. We got to guess something. So we've got 3 members coming into this joint. We've got that force in AB that we figured out the magnitude of it as 0, looking at that method of joints at joint A, but I'm going to put it in there just to be explicit about it. And then we've got 2 other members that we're going to assume are in tension here. We've got that force that's being transmitted in member BC, going from B to C, and that's straight horizontal. And then we've got this other diagonal member, this force that's being transmitted into member BD. And this member is orientated at that traditional 4-3-5 triangle that we can see. Okay, so every 4 units that we go over, we go down 3 units, resulting in a hypotenuse overall magnitude of 5. So just by a quick little inspection, we can see if we do some of the force in the Y, we can solve for that member in BD real quick. So if everything's in equilibrium, we got this BY, that reaction at that hinge support going up, so positive. We got this member for AB. Yes, it's 0, but we're going to label it anyways. And then we've got that force in that Y for every 3 units that we go down. Overall 5, so that ratio is going to be 3/5 of that force in BD. Ooh, and we know BY and we know AB, so we're going to just rearrange this equation real quick just to solve for that member in BD. And it comes out positive. So we guessed the right direction. It is in fact in tension. Sweet. And it's got a magnitude of 75 kilonewtons. So 75 kilonewtons in compression. In tension. Oops, game's out positive. Okay, now we're going to do some of the forces in the X equals 0. And we've got that force in BC going negative. We got that BX component going positive. And then we've got that force in BD going negative as well at a rate of 4/5. Sweet. And I'm just going to rearrange this equation and put all our knowns on one side of the equation and all our unknowns on the other side of the equation. So we've got that BX at 60 kilonewtons, and we solve for that force BD above, doing some of the force in the Y. So that's 4/5 of that 75 kilonewtons, and something amazing is going to happen here. I'm going to plug this in our calculator. We're going to find out that that force in BC is 0. Amazing. Math of magic. Math is our friend, you guys. It's a little bit weird, but hey, it's not going to lie to us. And we're just going to pretty this up so that we've got it all summarized and all clean and nice. And then we're going to move on to our other joints to solve for those as well.